let's talk titrations. A titration is when a solution of accurately known concentration is added to a solution of unknown concentration until you get a completed reaction. In limiting reactant terms, until your limiting reactant stuff both run out. So here's what a titration looks like. Hopefully you have performed one previously, maybe in a lab last term, maybe in a high school lab if you had access to lab facilities in high school, or maybe you've only done one in a virtual environment, but hopefully you've been exposed to a titration before. Down here in this Erlenmeyer flask is our solution of unknown concentration. Up here in our burette is a solution of known concentration, and we drip, drip, drip the thing from the burette in slowly until it changes color. So let me explain a little bit. This particular thing, because of the sentence I've written here, we're going to have base in our burette, we're going to have acid in our Erlenmeyer flask, and we drip, drip, drip that base into our acid until the reaction turns pink. The reason the reaction turns pink is because of an indicator in solution. When the reaction turns pink, that's known as the end point of your titration. The end point is sometimes known as the equivalence point as well. To me, there's a slight difference in calling something the end point and equivalence point, but most people use those words interchangeably. But the end point, equivalence point, that's the point where it changed color. That signals the end of your reaction. It signals the end because you've added an indicator. The indicator is the thing that changes color. Indicators themselves are weak acids. So this is an indicator known as methyl red. And when this compound has this H on it, it appears as a red color. When it goes through an interaction to lose an H, note there is no H on that nitrogen anymore. When it loses an H, because acids donate H's, when it loses an H, it turns yellow. We have to have added enough base to solution to react our unknown acid, but we add one extra drop to turn our indicator from an acid into its conjugate base so that we can signal this color change. Phenolphthalein is another common indicator. It's the reason our reaction in the previous slide turned pink. This version is the colorless version. It's because there's this H in the weak acid version, in the acidic form, and it has lost this H in the conjugate base. Indicators themselves are weak acids. So when we're doing a titration, in order to get it to turn pink, we have to have added enough base to react our unknown acid, and we add one more drop of base to turn our indicator from its acidic version into its conjugate base so that we get this color change signal. Okay. A typical titration curve looks like this. We're going to talk quite a bit about titration curves, but they have pH on the y-axis and volume on the x-axis. Since this one starts at a low pH and pH increases over time, I know that that means I've got this sort of setup where my Erlenmeyer is going to have acid in it, and my burette, you're going to love my drawing skills, my burette has base in it. That's because I'm measuring the pH of this solution. So it's the pH of the Erlenmeyer over time. So that Erlenmeyer will become more basic over time as you drip, drip, drip more base into that thing. So you should be able to, you will be able to, look at a titration curve and know, oh, that's an acid being titrated by a base because it starts at low pH and ends at high pH. Furthermore, this midpoint where you go up this steep slope, this midpoint is the actual equivalence point, the end point. It's the point where you've added precisely enough base that in this Erlenmeyer in the bottom, the moles of acid of your unknown acid that you began with is exactly equal to the moles of base that you have dripped in. So at the end point, at the equivalence point, moles of acid is equal to moles of base. Can you reverse this system and have a base down in this solution and an acid up there? Absolutely. But at the end point, at the equivalence point, the moles of acid is equal to the moles of the base. It's a little bit of a different type of question here, but if we're starting out with base in the bottom, base in the Erlenmeyer, our pH curve is going to look more like, our titration curve is going to look more like this guy, starting at a high pH, ending at a low pH. That's still my equivalence point. That midpoint of your steep slope part is the equivalence point. That's where the moles of acid is equal to the moles of base. Okay. Why do we put these little colored things on here? Well, I'm showing you that methyl red switches color at that point right there. Switches from red to yellow at this pH. Phenolphthalein switches from colorless to pink at this pH. So neither of these indicators is perfect, that it swaps right at this exact midpoint, but they're both pretty close. And so when you have done a titration and overshot your titration, meaning you turned your color too dark, often pink, you go too pink, it probably means you added one extra drip and all of a sudden you're up here on the titration curve rather than down there. So your volume added is going to be totally wrong and your mole calculation is going to be totally wrong. You want to hit that point as close as possible, so you pick an indicator that hits that point as close as possible. Okay, I'm talking too long on these things. We got more work to do. Titration is a technique for counting moles. We're going to have a titration that we have a known concentration of something in our burette and an unknown concentration of something in an Erlenmeyer. It could be an acid or a base in either of those, and there are other types of titrations too, actually. So one of the things that we can use a titration for is determining molar mass. Molar mass has the unit of grams per mole, and titrations are a great way to count moles. So we can determine this bottom number from a titration, and if we wanted to find molar mass, we can weigh this amount in the lab. And so something that you may have done last semester is this exact type of thing where you have an unknown acid, you weigh out a certain amount, dissolve it in water, and then do a titration of it. Knowing how much base you add, you take advantage of the equivalence point, means moles of acid is equal to moles of base, and then you know how much acid you got. Let's see this in action with some numbers. 3.664 grams of monoprotic acid was dissolved in water. It took this much of this much solution to neutralize the acid. Determine the molar mass of the acid. Determine the molar mass. That means we need to know grams, already got the grams, and we need to know moles. When I read a titration problem, I think in terms of pictures, and I would encourage you to think in terms of pictures. This monoprotic acid was dissolved in water, so I'm putting my acid in there. And I'm putting base in there. I'm putting 0.1578 molar sodium hydroxide in that burette. And I know precisely that it took 20.27 milliliters of this base to neutralize the acid. So, 0.02027 liters of base times 0.1578 moles of sodium hydroxide per 1 liter of solution times 1 mole of sodium hydroxide. I should probably write an equation per every 1 mole of monoprotic acid. Sure, that's helpful. That would tell me moles of acid. I do that math and I find I've got 0.0032 moles of acid. So I divide that grams by 0.0032 moles of acid, and I get a large molar mass of 1145 grams per mole. That's large. Most of the things we've seen, most of the acids we've seen are not that big, but that is reasonable. Some organic acids are very large molecules, so that's reasonable. Okay, I said I should write an equation, and I didn't. What would my equation be if I had written one? I'm adding strong base, so that means hydroxide, to an unknown monoprotic acid. You guys don't love generics, but it's an unknown monoprotic acid. Strong base plus weak acid, limiting reactant because strong base And if either reactant is strong, it's limiting reactant, we're going to create A minus and water in this solution. So the reason that I would have considered that I might need to consider this equation is to find this mole ratio, 1 hydroxide for every 1 acid. Yeah, it could be 2 hydroxides for every 1 acid if it's not a monoprotic acid, but we're not quite there yet, but we will be very soon. Okay, I told you, I think in pictures. I really would like to encourage you to think in pictures. If I have this titration curve, this starts at a high pH and ends at a low pH. So the first thing I'm ready to say is I've got a base being titrated by acid. Looking at this curve, high pH to low pH, base being titrated by acid. Something that I maybe should have said previously is depending on the pH of this endpoint, if the endpoint pH is exactly at 7, that's going to be a strong base titrated by a strong acid, or a strong acid titrated by a strong base. Depends on who's in the Erlenmeyer and who's in the burette. But if your pH is less than 7, it's going to indicate one type of reaction, and I'm not going to say what right now. If your pH at your equivalence point is greater than 7, it's going to indicate another type of reaction, but I won't say what right now. We are going to go there, but now it's not the time. Okay, what is this a picture's worth 1,000 words kind of thing? Well, there are 4 different situations I can find myself in when I have a titration problem, when I have a titration curve, lots of titration things. Situation number 1, it doesn't look visible, but this point is labeled as situation number 1. That's measuring the pH of just this solution. The only thing present at picture number 1 is weak base. So my beaker, oh boy, you love pictures, my beaker would be all B's in solution. The number of molecules that you put in your picture is not super important, but I like 4 for a reason that you'll learn in a minute. But I like 4 little B's in my picture. Situation number 2, the number is back there, but it's not visible. Situation number 2, what has happened is I have added some strong acid. Strong acid has been added. So I still have weak base in solution, but I have also created some conjugate acid of my weak base. So at point number 2, my limiting reactant table would look like this. B plus H plus, I've added strong acid, yields BH plus. Limiting reactant would say, because of exactly where that one is, if I've added 0.1 moles of this, or if I started with 0.1 moles of this, 0.05 moles of that, I'm just making up numbers over here, minus X plus X. At the B point, at the point number 2, here's where I'm at. I've got equal moles, I say equal and I start writing equal. I've got equal moles of base and acid present. Because it's halfway to my equivalence point is at 50 milliliters, at the halfway to my equivalence point, I've got equal moles of base and acid. I'm not going to write that I've got equal moles, but at this specific point number 2, I've got BH plus, 2 of them, and B's, 2 of them. Half of my B's have reacted to become BH plus. Okay, that's situation number 2. Situation number 3. Situation number 3 is the equivalence point. It's the point at which I have added precisely the exact amount of strong acid as I started with weak base. And the limiting reactant table would have 0, 0 for both reactants, and you would have all weak acid in solution. You only have BH plus. So if I squeeze a picture number 3 over here because I'm a big writer, I have 4 BH pluses in solution. And then picture number 4, I have now started to add extra strong acid. So I will have leftover strong acid at the end of my picture number 4. I'm going to erase my limiting reactant table because that's where I have real estate to write. Picture number 4, beaker number 4 would have all BH pluses, 4 of them. We don't start consuming those because you can't make an acid any more acid. But you've started to accumulate some extra H plus in your beaker. So, this titration curve, you can find yourself in 4 possible situations. These are what the 4 pictures would look like in your 4 possible situations. One little thing before we move along and actually answer the question that's asked here. Anywhere before the equivalence point, but after the instant that you start dripping in solution, anywhere along that curve, you're in situation number 2. At the precise moment where you're halfway to the equivalence, that's how your picture looks this way. But if you're in, let's put another number, point number 5, you're going to have a mixture of BH plus and B at point number 5. Come on, PowerPoint. You're going to have a mixture of BH plus and B, but your ratio will be different. At point number 5, you're going to have maybe 3 Bs and 1 BH plus. That's because some of your base has reacted, but not a lot. If you were at point number 6, it's going to be the opposite ratio, like 3 BH pluses and 1 B, right? Right. Okay, let's actually answer this question that's behind here of the curve on the left results from the titration of this with this. What's the estimate of the value of pKb? What? Well, the reason I highlight point number 2, besides to tell you what I just told you, at point number 2, that's where the moles of weak acid and weak base are equivalent. At point number 2, that's where you've hit this magical buffer point where your pH is equal to pKa plus 0 because it's plus the log, come on, this PowerPoint is so slow today, plus the log of base over acid. So in this case, it would be B over BH plus. Come on. It's so frustrating. So at this magical point where it's log of base over acid, where those are equal, this is 1, log of 1 is 0, so pH equals pKa. At point number 2, pH equals pKa. So if I do a little estimation at point number 2, that intersects along the y-axis at pH 9. So the pKa of this compound is 9. So that means the pKb of this compound, which is what they're asking for, is 14 minus 9. So the pKb is 5. Okay, I've been talking for a long time already. I promise we're about to get to some more math. Don't be sad. If you have a weak acid titrated by a strong base, the weaker the acid, the smaller the equivalence point inflection. What the heck is that? The smaller this little curve bit gets. So a strong acid has a very steep, very sharp slope to go from low pH to high pH. The weaker the acid, though, the less steep, the less severe this inflection point becomes. For very weak acids, it's not possible to detect that inflection. We're going to stick with acids probably on these kinds of scales so that we can detect the inflection point, but for very weak acids, it's not possible. All right, I promised math. Let's do math. We're going to do math along with pictures. Ooh, our favorite. 25 milliliters of this is titrated with that. Calculate the pH at these points. In my head, I see the picture of the titration first, and I got to get that straight, of who's where. Why did I put the volume up there? I don't know. Who's where, what's in the burette. So that helps me know how to get started. This is titrated with that. So that means HCl is in my burette, and methylamine, that's what that is. You don't have to know the name of that guy. But methylamine is in that Erlenmeyer flask. Methylamine is a base being titrated by a strong acid. So did I say that base is strong or weak? No. But is it one of the 6 strongs that you memorized? No. So it's a weak base. So in my head, things that I'm thinking in my head before I start doing any math is I've got a weak base being titrated by a strong acid, and I can see a curve that's going to start at high pH and end at low pH, right? Weak base being titrated by strong acid, all right? That's getting my thoughts together before the math. Let's do math. Okay, at the very beginning of the titration, before you have added any acid, the only thing present in solution is weak base. So if I drew a picture, I would draw CH3NH2. CH3NH2. And because I've already told you I like 4 little molecules, I'm going to write 4 little molecules of these guys. That's the only thing in solution. So CH3NH2 is not going to do a limiting reactant thing. It's a weak base that can react with water in an equilibrium fashion to produce small quantities of hydroxide and small quantities of the conjugate acid, CH3NH3 plus. I should put aqueous on all these things, but I didn't. This is not a limiting reactant table because we have not yet added any strong stuff. This is a simple rice table, a simple Kb calculation. If it's 0.1 molar this, none of that, plus x, it feels like so long since we've done this, that's x squared over 0.1 minus x, I'm getting there, over 0.1 minus x equals Kb, which is 4.4, times 10 to the negative 4. We can forget this bottom x because it's small, because K is small. Solve for x. X equals, where's my notes? X equals 6.63 times 10 to the negative 3. So if we're told to find the pH, that would be minus the log of 6.63 times 10 to the negative 3 equals POH. POH is 2.18 according to my notes. 14 minus that, pH is 11.82. 11.82. So in addition to calculating pH, we're going to draw a titration curve. So I'm going to make it a pretty reasonably large one. And at 0 milliliters of base added, milliliters of acid added. I shouldn't have made it so large where you can't read the x-axis. And pH, we're starting out at 11.82. Right there on that y-axis. Okie dokie. B says 10 milliliters of 0.1 molar HCl has been added. All right. We're going to switch colors so we can maybe follow along a little bit easier. I don't know if it will help. Point B, 10 milliliters of 0.1 molar HCl has been added. So that's 0.01 liters of HCl times 0.1 moles of HCl per 1 liter equals 0.01 moles of HCl. Oh, at least I can amuse myself. That's strong acid reacting with our weak base in solution in a limiting reactant way because it's strong acid to create CH3NH3+. All right. This must be a limiting reactant which starts with moles and ends with moles. And it changed in the middle. 0.001 moles. And I just realized I did not previously calculate. 0.025 times 0.1 moles. Sorry, maybe you can follow along without me having to write that one out because I'm running low on real estate here because I write so big. 0.0025 moles of methylamine. None of this, none of that. Nope, not none of this, none of that. That's just what I always say. Oh boy, this is going to be a hot mess. None of this. This runs out. H plus is limiting. 0.0015. 0.001. Okie dokie. So the picture of the beaker in the solution is always the picture at the end of a limiting reactant table. If you have to do a limiting reactant table, the beaker picture should be the picture at the end of your limiting reactant table. So we definitely have some CH3NH2. We also have some CH3NH3 plus. We've got more of the CH3NH2. Do I have to give it super accurate ratios? No, but I want to show more CH3NH2. That's why I choose an even number of particles so that I can say there's more of this thing than that thing. So that's what my beaker picture would look like. And then I need to calculate the pH of the solution. Holy moly. Well, I can recognize that, I've got some of this, which is a weak base, and I've got some of this, which is a weak acid, and they are a conjugate pair. I've got a buffer solution. So I could go forward with flipping this thing around, doing an equilibrium table, a Rice table, calculating pH from there, or I can recognize it's a buffer and know that pH equals pKa plus the log of base over acid, and in this system the base is CH3NH2, CH3NH3 plus. So that becomes, we know Kb is this. So I can negative log that thing to find pKb, and then I 14 minus that to find pKa. So that becomes 10.64. Maybe you followed along. Minus the log of the Kb, 14 minus pKb equals pKa, yeah, plus the log of base over acid, 0.0015, 0.001. My pH should definitely come down after I add strong acid, and I get, we'll put it way up top, pH equals 10.82. This system, 10.82. So if I go back to my plot at 10.82, my scale is not going to be awesome here. This is after 10 milliliters of base. Oh, let's actually make this a little stretched out. 10 milliliters of acid. I'm connecting my little dots. I'm going here. All right, we're on the way down. That's point B. We drew the picture, we calculated the pH, we added it to our plot. When 25 milliliters of HCl total has been added, that's point C. 25 milliliters, 0.1 molar HCl. So that's 0.025 liters times 0.1 moles per liter. 0.0025. It's strong. Do a limiting reactant table. It should start out a lot the same as the last one. This plus weak base. Limiting reactant, CH3NH3 plus. Start and end with moles. I've got 0.0025. 0.0025. 0. Minus X. Nope, that's a plus X. Minus X, minus X. Ooh. Both reactants ran out at this limiting reactant table. That means we have reached our equivalence point. That should be point. Equivalence point. We have reached our end point, our equivalence point, where the moles of base is equal to the moles of acid that we've added. So, our beaker picture should always be at the end of our limiting reactant table, what's in solution? Well, at the end, we've got all weak acid in solution. So we should have 4 little molecules of CH3NH3 plus. They're kind of spilling out of my beaker a little bit because I write too big. 4 molecules of CH3NH3 plus. This is all weak acid. How do you calculate the pH of a solution of all weak acid? With a Rice table. I'm going to have to flip to a new slide. I really am such a big writer. A Rice table. where I start with all weak acid and I write a standard Ka equilibrium. It's just the reverse of the limiting reactant equation we just did. Hopefully we did enough practicing of our solubility precipitation reactions that this feels like we're repeating the same process, because we are. Yeah. So I need to know concentration instead of moles in a rice table. So that's 0.0025 moles divided by, now we've added a total volume of 50 milliliters, so 0.05 liters. So my concentration of CH3NH3 plus is 0.05. None of this, none of that, because they ran out at the end of my limiting reactant table. Minus X plus X plus X. This is a standard, like I said, Ka. 0.05 minus X equals Ka, and we were only given Kb, but the Ka is 2.27 times 10 to the negative 11. X equals 1.065 times 10 to the negative 6. So my concentration of H plus is X, 1.065 times 10 to the negative 6. Negative log of that thing equals pH equals 5.97. Ooh, isn't that lovely? 5.97. Okie doke. We go back to our handy dandy plot. And when we've added 25 milliliters, let's see if I can make it accurate spacing. It's probably not great. 5.97. That's my equivalence point. So I should come down, not so sharp, and then take a sharp dive to my 5.97. So the pH will gradually decrease, gradually sharp to 5.97 at the equivalence point. And then we're going to tail on out of here for our next point. Oh, going backwards. So many clicking around on so many slides. 35 milliliters of HCl total. 1, 2, 3, 4. So many slides. 35 milliliters of HCl total. That's point B, 35 milliliters HCl. 0.035 liters. 0.1 moles per liter. 0.0035 moles H plus. It's strong. Do a limiting reactant table. We've got strong acid plus weak base yields limiting reactant CH3NH3 plus. It's the same equation every time I do this limiting reactant table because I'm continuing my titration. This should be end. My brain is getting tired of talking and your brain is getting tired of listening. I know. We're about to wrap it up. 0035, 0025, none, minus X plus X, 0025, 0, 001. Okay. This time, I'm in the situation where I've got excess strong acid. Excess strong acid is going to be responsible for pulling the pH way down low. We've got weak acid in solution, but it's the strong acid that's responsible for pulling this pH way low. My beaker would have the same 4 molecules, because we haven't started reacting them away, like that's not a thing, the same 4 molecules of CH3NH3+, but this time NH3. This time we have to add an extra, at least one extra, H+, because we've started to accumulate excess strong acid. So how do you calculate the pH of a strong acid solution? You need to know the concentration of strong acid. We know we've got 0.001 moles of H+, strong acid stuff. Divide that by 65, nope, not 65, 25 and 35, yeah. No, not 65, sorry, brain fart. 60, we've added 60 milliliters, yeah. Can you add? Oh, yes, I can. 60 milliliters, so 0.60 liters of total volume. That gives me the concentration of H+, as in strong acid H+. that's 0.0167 molar. So the pH is minus the log of that. The pH is 1.78. Once you start accumulating excess strong acid, that pH dips very deep quickly. So if we go back to our plot page, when we've added 35 milliliters, we're at pH 1.78. That's real small. It should slope down like a little bit and then pretty sharply turn to our point over there. A long video. Titrations are important. They're hard problems. I get it, but we can do it. We got to do it. All right. Goodbye.